Hello and welcome to this series of training videos on residual uncertainty assessment. These videos are designed for practitioners, project managers and senior users who are interested in using residual uncertainty assessment, and they accompany the supplementary guidance and tool that has recently been released. Before we get into the training package, just wanted to introduce the project team that delivered the guidance and tool. So myself, I acted as a project executive on the Environment Agency side, alongside Louise Glover as our senior user. For Jacobs, our supply partners in delivering this, Rachel Lewis was their project manager, and the rest of the project team was Adam Parks, Richard Crowder and Phil Crawford. And Adam and Phil will introduce themselves in just a second as they're delivering these videos with me. Hi, I'm Ian Perkins. I'm a Senior Technical Advisor working on modelling skills development and quality assurance in the Environment Agency. I've worked for the Environment Agency for about 15 years across a variety of hydrological and hydraulic modelling projects. In recent years, I've focused on modelling improvements, working on our model standards and skills. On this project, my role was as project executive and making sure that we were getting the outputs that we needed for the Environment Agency.
Hello, I'm Adam Parks. I'm a technical director at Jacobs, and I supported this project as project principal, providing technical advice and support to Phil and the wider team, building on my 20 years experience in flood risk management across the UK.
Hi, my name is Phil Crawford. I'm a Principal Flood Risk Management Specialist at Jacobs. I've got over 10 years consultancy experience, and I'm the lead author and technical lead for the Supplementary Guidance project.
So the core objectives for this series of training videos is to provide an understanding of residual uncertainty assessment, hereafter referred to as RUA, and its importance in modelling and decision-making processes. It's to equip participants with the skills to identify, assess and respond to residual uncertainties effectively, to encourage the adoption of best practice in managing and communicating modelling uncertainties, enable participants to apply RUA methods and tools in real-world scenarios, enhancing their practical knowledge and confidence, and to promote collaboration and knowledge sharing among participants, fostering a community of practice around RUA. So in terms of the course content, we've broken it down into 4 chapters. Chapter 1 is going to be an introduction to residual uncertainty assessment. So we'll cover why we consider and assess uncertainty and what is residual uncertainty assessment. In Chapter 2, we'll look at the supplementary guidance, look at the purpose of the guidance, why it was created and what's actually included within it. And then we'll look at the applications that we use residual uncertainty analysis for. In Chapter 3, we'll look at the residual uncertainty assessment methods themselves. We'll have a look at the overview of those methods and how they're calculated, and we'll review a series of case studies. And then in Chapter 4, we'll look at the residual uncertainty assessment tool. We'll provide an overview of the tool and a demonstration. Just a quick glossary of the terms before we get started. We use quite a few technical terms and some abbreviations throughout. The key abbreviations that we repeatedly use are provided here. Chapter 1, Introduction to Residual Uncertainty Assessment. So why consider and assess residual uncertainty? So in this section, as our learning objectives, we'll recognise why it's crucial to consider and assess uncertainty in modelling and decision-making processes. We'll identify the challenges associated with measuring, communicating and managing modelling uncertainty. We'll look to understand the Environment Agency's requirements for residual uncertainty assessment, and we'll appreciate the impact of uncertainty on the model outcomes and decision making. And we'll develop strategies to effectively address and mitigate uncertainty in your work. So why is it important that we consider and assess uncertainty? Well, we know all of our models are subject to uncertainty. We recognise that a lot of the input variables that we're selecting, we don't know what their real values are, and in general it's good practice for us to make an assessment of how large those uncertainties are. Most of the time for the modelling that we do for the Environment Agency, we're making a best estimate of the risk. And we have to ask ourselves the question, is that best estimate of risk enough? And the answer is it's going to depend on what it is that we're trying to assess. In simple terms, the assessment should be proportionate to the consequences of getting our risk assessment wrong. So if we're assessing the risk to protect something like a nuclear power station, the consequences of failure are very high, and we're going to have a very low tolerance to the uncertainty there. We do not want that assessment to be wrong. So we're going to undertake a detailed assessment. At the under the scale, something like a natural flood management intervention and an upland catchment, there's a very low consequence to failure there. So our best estimate is almost certainly going to be enough, and maybe we don't need to conduct any modelling at all. For the majority of modelling that we do for the Environment Agency, where we're doing things like building flood defence schemes, they're going to fall somewhere in the middle of this kind of continuum. So we need to be certain we can undertake some level of uncertainty assessment and provide some confidence in the standard of protection and provide some confidence in the investment that we're making, but we always need to make sure that we're being proportionate to the risk. So there's key considerations. What's the tolerance to uncertainty? What's the consequence to failure? Are we providing confidence in the standard of protection? And are we being proportionate to the risk? So we know it's important to assess the uncertainty of our models, and yet these techniques are not being used routinely outside of where they're mandated. This is largely because measuring, communicating, and managing model uncertainty is challenging. Let's have a look at some of those challenges in more detail. Measuring model uncertainty is seen as complex. Often, not enough data is available to make a complete assessment, which leads us to making assumptions. Which sources of uncertainty to include or exclude is a subjective decision, which is often guided by the available data and expertise that we've got. Prior to the supplementary guidance, there was also a lack of clear standards to work within for RUA methods to help steer you on how wide the uncertainty bounds should be for particular variables. All of this subjectivity led to a lack of consistency in our assessments. Communication. We're often unsure how to communicate the uncertainty. As evidence practitioners, we naturally don't want to reduce confidence in the tools we've built to help make flood risk decisions. We can often feel like just acknowledging model uncertainty with decision makers and a community at risk from flooding opens us up to challenging questions on the validity of our approaches and the results that we've provided. When we speak qualitatively about uncertainty, the language that we use can also introduce ambiguity if we're not careful. We can speak about having high confidence in something, but that can mean different things to different people. So we need to quantify our uncertainty, but we need to do it in a way that's consistent and accessible for a wide range of stakeholders. Managing uncertainty. There's previously been a lack of clarity on the roles within the RUA process. The supplementary guidance makes it clear that modelers have a key role in evaluating what we do with uncertainty information. Modelers understand the data and the tools used more than others, so need to be closely involved in supporting the decisions on what response is appropriate to that uncertainty. When making those management decisions on what the appropriate response should be, there are three common issues that come up, which we need to decide how to manage. Firstly, the issue of over-design can come about. This arises out of a desire to be conservative and cover all of the uncertainty. This can naturally lead to increasing costs of a scheme and potentially make it unaffordable. Secondly, where we can't quantify all of the uncertainties, it can lead to us deciding just to apply some standard tolerances instead. This might lead to the opposite problem of under-design and leave us open to challenge. Thirdly, it can leave project teams feeling unable to make decisions and move forward with confidence. This can often lead to calls to gather more data and cause project delays. So you can see that there are subjective decisions being made across each of these three areas. The RUA supplementary guidance seeks to standardise our approaches in decision making to ensure that we're being proportionate in our approach to managing each of these. So what are the current Environment Agency's requirements for residual uncertainty assessment? The requirements are set out in our internal policy guide lit 16921. This sets out a requirement that at FCRM appraisal at the outline business case stage, three things should have occurred. A residual uncertainty assessment that's been led by modelling specialists. It should provide a register of uncertainties, and it should provide a residual uncertainty calculation record. These are the minimum technical requirements at outline business case stage, but the best practice that we recommend within supplementary guidance, and we'll discuss it further on in this training, is that some of these activities are started and considered earlier in the appraisal process. So in this section, we've learnt about the critical role of uncertainty in modelling decision making. We've looked at the challenges of measuring, communicating and managing uncertainty, and we've looked at the requirements set out by the Environment Agency for RUA.
Now that you've understood the importance of residual uncertainty to projects, let's dig a little deeper into what RUA is and how we calculate it. There are 4 learning objectives associated with this section. The first is to understand what residual uncertainty is. Secondly, the principles around a residual uncertainty assessment. What the RUA life cycle is, identify, assess, respond. And finally, an introduction to confidence intervals and their importance. On this slide, I'll explain what residual uncertainty is in the context of a scheme. Using a simple example below, we're going to build a linear defence on a river system to reduce flood risk to a certain area. Just to note, RUA can be applied to any type of flood defence scheme, not just linear defence schemes, though with some limitations which we'll talk about in later slides. When we're looking to build a linear defence, the height and the design of that defence considers many different aspects. One of those is uncertainty. Typically, we'd use a hydraulic model to assess a river system and derive the design water level for a linear defence. This could be a given return period, such as the 1 in 100-year event, for instance. We wouldn't just build the linear defence at that design water level. We'd also want to consider the uncertainty in that design water level using a residual uncertainty assessment and adapt to that uncertainty. One typical adaptation for a linear defence scheme is the addition of a freeboard to the scheme design. This is a height of wall above the design water level, which makes an allowance for that uncertainty, giving us greater confidence that the scheme will provide the standard protection it's designed to do. This is a good point to talk about uncertainty, confidence intervals and standard deviations and what they mean to a standard scheme. For this example, I'm going to look at a linear defence option. This is where we're building, say, a wall adjacent to a river to stop flooding to an area of the floodplain. Typically what we'll do here is use hydraulic models and hydrological calculations to estimate our best estimate of what that design water level will be. So if my scheme was to provide a 1 in 100-year standard protection, a 1% AEP standard protection, then I'd calculate that water level and build my scheme to that height. If I look at the probability distribution, that estimate has no allowance for uncertainty, so it lies right in the middle of my statistical distribution. That means that should the 1 in 100-year event occur at this location, there'll be a 50% chance that water level will be lower than my scheme height and a 50% chance it will be higher. Therefore, I've got a 50% chance at any given 100-year event that the scheme will be defeated and resulting in flood risk to properties behind it. This is why residual uncertainty is so important. It allows us to manage the amount of risk we're comfortable with applying to our schemes based on the consequences of that overtopping. If I wish to reduce the risk of overtopping due to uncertainty, I could assess my residual uncertainty using one of the methods we'll talk about later in this section, and perhaps calculate the 1 standard deviation or 68% confidence interval at that location. This lies far to the right of the centre point of my distribution, and as a result, should the 1 in 100-year event occur at this location, there'd only be a 16% chance of it overtopping. This does result in a far higher flood defence because I'm having to add height onto that flood defence as freeboard to allow to adapt to that uncertainty. Depending on the consequence of my appetite or my acceptance of uncertainty, it may be I need to go even higher. It may be I need to look at the 2 standard deviation, which will reduce the chance of overtopping to 2%. As Ian was saying earlier, decisions around how much allowance to make for uncertainty are project specific. They need to be proportional and take account of the consequences of a failure of that asset. We're a lot more accepting of failure for a small upstream natural flood management intervention like a leaky dam than we would be for a failure at a nuclear power plant station. There are 5 key principles to residual uncertainty assessment, and these were set out in the document Accounting for Residual Uncertainty, an update to the Fluvial Freeboard Guidance, which was published in 2017 and remains a key reference document for this topic. Those principles are: 1. Challenge the credibility of the system components. What this means is where we assess uncertainty associated with each component that makes up a system. That may be the hydrology, the hydraulics, our topographic survey, and so on. These are the areas where there is uncertainty which we need to evaluate. 2. Consider the reality of the present day. What this means is we assess uncertainty as it stands today. We don't take account of climate change in this assessment. That's dealt with by separate guidance. Number 3, explore a range of measures to manage uncertainty. There shouldn't just be one measure to manage uncertainty. In the previous example, I talked about applying a freeboard to a linear defence to allow for that uncertainty. Other approaches may have been taking additional measurements to reduce the uncertainty in a hydrology, perhaps setting the defence back to create more floodplain storage, reducing the impact of that uncertainty, and so on. 4, ensure a proportional response. Any response to uncertainty is proportional to the objectives of scheme or strategy. Ultimately, we want flood defence schemes to be progressed and built, and any response to uncertainty is proportional to those schemes. 5, effective management of uncertainty is a continual process. We'll look shortly at the life cycle of residual uncertainty and explain this concept in more detail. This slide sets out the residual uncertainty life cycle and is particularly relevant to FCRM scheme appraisal. It consists of 3 sections: identify, quantify, respond, and it's not linear. This process is a cycle and may be repeated several times during a project. The first section relates to identify. This is where we identify sources of uncertainty which may impact on our scheme design. Typically, these relate to hydrology and hydraulics, which directly inform your design parameters, such as the height of a defence or the volume of storage required in a storage reservoir. Those uncertainties may relate to things such as the length of record of river gauge, which informs your hydrology, age of your topographic survey, which influences both the hydraulic model and your scheme design, as well as other parameters such as tide. So if you've got a tidal or estuarine scheme, your estimates of peak tidal levels are particularly important. Once you identify these sources of uncertainties, and again, it's important you do those as early in the scheme as possible, you can move on to quantify. This is where we use one of the 3 methods outlined later on in this presentation to calculate the uncertainty associated with all those sources of uncertainty. So the Tier 1, the Tier 1.5, and the Tier 2 method. Those convert those uncertainties into, for instance, a level of uncertainty as a linear defence. Once we've quantified the uncertainty, we need to respond to it. The response is broadly broken into 3 types. Further analysis, so if we've got a hydrological analysis which has got a significant amount of uncertainty associated with it, can we do further calculation or investigation to reduce that uncertainty? Can we improve our hydraulic model, for instance? Data collection. We may have identified that a source of uncertainty is the quality or age of topographic survey at a location. So an obvious response would be to go out and collect more survey, refresh that survey, and update our analysis accordingly. Other data collection options may include putting a gauge or a temporary logger into a location to gather additional data for calibration or hydrological calculation. Finally, we've got scheme adaptation. This is where we do things such as adding freeboard onto our scheme height to respond to that uncertainty. But that shouldn't be the first approach. Each time we collect more data and take further analysis or change our scheme design, we should consider whether we need to repeat this cycle in order to better understand the uncertainty. So as more data is collected, we may wish to repeat the uncertainty assessment so we better understand what impact that's had on our uncertainty. Just to recap on the learning objectives from this chapter, we've discussed the principles of residual uncertainty assessment, the importance of understanding and assessing residual uncertainty in our models and decision-making process, particularly around FCRM projects, the steps involved in the residual uncertainty life cycle, including assessing, identifying, and responding to residual uncertainties, and find the significance of confidence intervals in quantifying and communicating uncertainty and their role in providing a range within which the true value is likely to lie.
Welcome to Chapter 2, Supplementary Guidance. This first section looks at the Residual Uncertainty Supplementary Guidance, how it fits in with a wider framework, and what's included and not included in that guidance.
So in this section, we're going to look at the Supplementary Residual Uncertainty Guidance itself. So we'll look at how the supplementary guidance sits within the existing framework of guidance and policies. We'll look at the background and context of the project that produced the guidance. We'll look at the purpose of the supplementary guidance and its significance in supporting the use of assessment. And we'll look at what's included in the supplementary guidance. Residual uncertainty assessment is a requirement for all FCRM appraisal projects. This requirement sits within and aligns to the wider policy and guidance about considering uncertainty within infrastructure projects. These policy and guidance documents include HM Treasury's Green Book, DEFRA's appraisal guidance, and the Environment Agency's technical guidance for appraisal. While the supplementary guidance has been developed for the Environment Agency and applies to England only, we invited our partners from SEPA and Natural Resources Wales to provide input into the guidance, alongside several of our major framework suppliers. This was to ensure that the approaches within the guidance are supported and have been reviewed across the industry and can be applicable more widely across the whole of the UK. So what is the RUA guidance? Well, there are two main pieces of guidance that now cover RUA. The 2017 Accounting for Residual Uncertainty Science Report was commissioned by DEFRA's Joint Flood and Coastal Erosion Risk Management Research and Development Programme. It replaced the older W187 Fluvial Freeboard guidance. It sets out 5 principles for RUA, which are discussed in Chapter 1 of this training package. It introduces methods for undertaking residual uncertainty assessment aimed at activities such as development planning, flood risk strategies, and flood risk scheme appraisal. These methods have subsequently been known as the development planning method, Tier 1 and Tier 2 methods. The science report also sets out methods for assessing the standard of protection of existing assets that incorporate uncertainty. The 2024 RUA supplementary guidance does not replace the 2017 guidance. This document is still the overarching guidance that covers the principles and methods of residual uncertainty assessment. The 2024 guidance is intended to provide clearer standards, processes and outputs for project teams that are implementing RUA. Their aim is to make the approach more consistent and easier to audit and assure. The 2024 guidance focuses on Tier 1 applications and also introduces a Tier 1.5 enhanced method. As the Tier 1 method assumes a linear relationship between variables, which rarely occurs in realities, practitioners across the industry have developed an extended or enhanced methodology since the publication of the 2017 science report. We have since adopted the term Tier 1.5 to describe this method. The enhanced method addresses some of the limitations of the linear approach, and through limited additional sensitivity analysis of variables provides a more robust solution. The supplementary guidance provides details on the application of Tier 1.5 methodology and describes best practice for when it should be used. The 2024 guidance now also provides details of the roles and responsibilities within the project team. It provides detailed case studies based on real-life scenarios that allow a practitioner to follow through all of the steps and decisions made in an RUA. And finally, the supplementary guidance provides an Excel-based tool for assessing RUA calculations in a consistent format, producing consistent outputs, and it operates as a template as well for producing a report on RUA assessment. Developing the supplementary guidance. The project to develop and write the supplementary guidance was driven by frequently asked questions about the application of RUA following the publication of the 2017 science report. The key objectives were to simplify the RUA process, provide consistent language, standards and approaches to all of the decisions within an RUA, and to provide consistent outputs and evidence records for an RUA through the calculation tool, the case studies and templates that were provided. A series of workshops were held during the discovery phase of the project to capture user needs from across the FCRM industry. User needs were then categorised and assessed to consider their priority and whether they met the scope of the project during a gap analysis and planning phase. During the writing and tool development phases, a steering group, again covering major framework suppliers and other UK regulators, provided peer review and user acceptance testing. The 2024 Supplementary Guidance is actually a package of 6 documents and the RUA tool. In addition to the Supplementary Guidance document, there are 5 standalone case studies, each covering different scheme types, environments and applications of RUA. These case studies are based on real studies but have been anonymised in the reporting. They cover fluvial linear defences using the Tier 1 method, fluvial linear defences using the Tier 1.5 method, coastal tidal defences, natural flood management and storage. These case studies can be used as a pro forma for your own assessments. They provide a clearly structured reporting template. And finally, the package includes the RUA tool itself. This spreadsheet-based tool assists in undertaking the calculations and providing spatially variable residual uncertainty allowances. More detail on the case studies can be found in Chapter 3 of this training, and a walkthrough of the RUA tool is provided in Chapter 4. Learning outcomes. In this section, we've learnt about the importance of understanding the background and context of the project that led to the development of the Supplementary Guidance, the significance of the Supplementary Guidance and its role in supporting efficiency, consistency and reliability of the application of residual uncertainty analysis, the identification of specific needs and gaps that the Supplementary Guidance aims to address, and we have an understanding of what's included in the Supplementary Guidance package and where the key information can be found. Applicability of RUA. In this section, we will learn to recognise where and how RUA can be applied in various contexts, and we'll look at the roles and responsibilities of different people involved in producing and making decisions around a residual uncertainty assessment. So in what situations should we use RUA and how should it be applied? As stated previously, RUA is mandatory for all flood and coastal risk management schemes in England, covering appraisal and design stages. The residual uncertainty documentation supersedes the fluvial freeboard guidance note and provides a range of appropriate measures to manage uncertainty, in addition to creating freeboard via crest raising. When applying RUA, it's important to remember the 5 principles discussed in Chapter 1. RUA does not expect you to account for all sources of uncertainty, just the most significant ones that can be quantified through analysis. While RUA must be considered for all schemes, how it is applied must be proportionate. It is not intended to block project progress. Where addressing the residual uncertainties adds significantly to the costs, careful consideration of the most appropriate response must be required. And whilst it works well for fluvial schemes, it can be more challenging to apply in some other circumstances, which we'll look at in the next slide. So there are environments, activities and systems where RUA is either not a requirement or has not been adopted. Coastal settings is one of the prime examples of this for coastal wave overtopping. In comparison to application of residual uncertainty assessment for fluvial linear defence scenarios, the application in coastal situations is often more complicated. Typically, 2 key elements must be considered in combination and accounted for in the design of coastal schemes. These are the still water levels and wave overtopping rates. The Supplementary Guidance concludes that in many cases the application of RUA is only suitable for coastal still water level assessments and should not currently be used for coastal wave overtopping. This advice is described in detail in the guidance, but it comes down to the potential to lead to over-design of schemes, as the Eurotop approach, regarded as best practice in the UK for calculating coastal wave overtopping rates, already accounts for some of the uncertainty variables, so there is potential to lead for double counting if RUA is used as well. Similarly, more research is required for us to better understand the uncertainty when applying RUA to many aspects of natural flood management. And as discussed in Chapter 1, because of the consequences of failure and how low they tend to be in NFM schemes, it may not be proportionate to consider RUA at all. RUA is also not currently used for new urban surface water systems. This is typically because they're designed with overcapacity to handle excessive rainfall events. This provides an inherent allowance for uncertainty. The 2024 guidance does, however, suggest that further research into the uncertainty associated with urban drainage over design would be beneficial. As well as these areas where RUA is not currently adopted within scheme design, there are several other FCRM activities where it could be used but currently isn't. These include flood risk mapping, land use planning, and the reassessment of existing defences. Whilst not fully covered, details of where the uncertainty may be present in these fields is discussed within both the 2017 Science Report and the 2024 Supplementary Guidance. Roles and responsibilities. One of the key issues around residual uncertainty assessment is who does what. Prior to the supplementary guidance, feedback from appraisal projects was that there was some confusion as to who was responsible for reviewing and making decisions around an RUA. Within the supplementary guidance, we've provided a RACI matrix covering the key activities and who is responsible, who is accountable, who should be consulted and informed at each stage. We've provided a description of the key roles described in this matrix and what competencies they should have within the guidance. The RACI matrix describes 3 stages of applying RUA within FCRM project appraisal and design, and the different roles involved at each stage. Stage 1 is undertaking the RUA itself, where uncertainty variables are selected and tested using Tier 1 or Tier 1.5 methods described in the supplementary guidance, and the residual uncertainty allowances are calculated for a range of locations and confidence intervals. The RACI matrix makes it clear that a modelling practitioner is responsible for undertaking the assessments at this stage. Stage 2 is the quality assurance process, decisions on selection of confidence intervals, and approval of a single residual uncertainty allowance value for each location. The RACI matrix steers that the client senior user should be responsible for leading this process and the decisions at this stage. They will most likely be supported by a client modelling subject matter expert who will assure the RUA calculations, and the project manager and project board who will ultimately be accountable for the uncertainty decisions. Stage 3 is applying the RUA results to your design and assessing its impacts. At this stage, a decision will be made on whether to accept and include the full residual uncertainty allowance in the design, or manage the uncertainty using other approaches set out in the 2017 RUA Science Report. The supplementary guidance steers that a modelling practitioner will be responsible for incorporating the allowances into the design and assessing the impacts, but the project manager will be accountable for the critical decision on how the RUA is incorporated and managed into the final project design. Although we've provided the RACI for clarity on roles in the 2024 guide, we've really emphasised in that guidance that realistically RUA should be a team effort, with everyone bringing their knowledge and experience to the table at each stage. Also, with improved reporting templates and the RUA tool to bring everything together, all of the required information should make the process of assuring and making decisions on assessment easier and more straightforward. In this section, we've learnt about the importance of recognising where RUA should be applied in various contexts, and we've learnt about the roles and responsibilities in the team for developing a residual uncertainty assessment.
Welcome to Chapter 3. In this chapter, we'll look at the methods available to assess uncertainty and also use some case studies to demonstrate how residual uncertainty can be calculated and what it means for a particular project. In this first section, we'll look at the methods available to calculate uncertainty in detail. The learning objectives for this section are to provide an overview of the methods available to calculate residual uncertainty, an explanation of each of the methods, including benefits and limitations, and detailed discussion over why to choose Tier 1.5 over Tier 1. As discussed in greater detail in Chapter 2, an assessment of residual uncertainty is required for all new appraisal projects undertaken in England. Whilst this guidance has been developed by the Environment Agency, we've worked with both SEPA, Natural Resources Wales and framework suppliers with a view to developing approaches that can be adopted more widely and for other project types. The 2017 guidance introduces 3 methods for assessing residual uncertainty, Planning and Development, Tier 1 and Tier 2. This guidance focuses on the Tier 1 application, which has been most widely adopted across the industry. As mentioned previously, in order to overcome the limitations with the Tier 1 method, practitioners have developed an enhanced methodology, termed Tier 1.5, which provides a more robust solution and estimate of uncertainty. Both the Tier 1.5 and Tier 1 methods are fully included within the supplementary guidance and the associated RUA tool. There are three recommended approaches for calculating residual uncertainty. The planning assessment method, which is most appropriate for early stage business cases such as initial assessment. The Tier 1 approach, which is most appropriate for strategic outlying business cases. And finally, the 1.5 approach, which is most appropriate for outline business case and full business case. It should be noted there is a Tier 2 approach. However, this is yet to be fully adopted within the industry, and we do not offer any recommendations on its use. The planning assessment method is the simplest of the methods available to calculate residual uncertainty for a scheme. It's quick and simple and particularly useful at early stage in the project. Looking back to the RUA lifecycle, this was the ideal sort of assessment to undertake at initial assessment stage, as it can help to identify areas of uncertainty which can be addressed before moving to SOC or OBC. The planning assessment method provides a coarse estimate of residual uncertainty and helps identify major uncertainty contributors. So, for example, whether the topographic survey is old or the hydraulic model is poorly calibrated. It's a qualitative, not a quantitative assessment, so it's very subjective depending who undertakes the study, and it's not required for land use planning. The process is quite simplistic. The user evaluates the sources of uncertainty within a project, having identified them, and grades them, in this case 1 to 5 stars. Depending on the level of uncertainty, you're given a guide to the amount of residual uncertainty you need to consider, both in terms of proportion of flood depth, so the extent of flooding, and the minimum depth, so the height of water. And that ranges from 900 mil to 300 mil. It's a very coarse estimate produced by this approach, and it's not suitable for detailed or later stage project assessments, certainly not in Environment Agency projects where a more comprehensive approach is required. The benefits are it's quick and easy to apply, so ideal for early stage projects, and it provides an early indication of potential residual uncertainty which will have to be addressed later on, as well as helping plan interventions that could reduce uncertainty, for instance commissioning new topographic survey or undertaking further model calibration or hydrological analysis. Now let's look at the broad approach to undertaking a Tier 1 or 1.5 assessment of residual uncertainty. Both methods follow the same process, and they deviate slightly in the calculation, which I'll talk about later. The first stage in both methods is to identify the primary variable. The primary variable is that design parameter that's most important to your scheme. So, taking an example of a linear defence, if I wish to build a flood wall providing a given standard protection, the primary variable will be the peak water level in channel adjacent to the defence for the desired return period. If I was looking for a upstream storage reservoir approach, then my primary variable may either be the pass-forward flow out of the reservoir or the volume of storage within the reservoir. Some schemes, if they're using multiple types of defence, may need to repeat the analysis for multiple primary variables. For this example, I'm going to use a primary variable, the linear defence example. So I'm interested in the peak water level in channel. Once I've identified my primary variable, I need to find secondary variables that may impact on that primary. These are the uncertainties I've identified earlier in the life cycle. Typically, they're things like the peak flow in the river from the hydrology, the roughness of the channel represented by a Manning's value, or the topographic survey that's got into my model. Once I've identified my secondary variables, I need to screen them out and define the confidences I have within each. So by this, I mean we look at each of those secondary variables, so for instance, my roughness in channel, and I work out how much confidence I've got in my estimate. Manning's roughness is a good example where there is good literature to guide you about what the uncertainties are for given standard deviations. So in the table above, you can see a chosen Manning's value on the first column, starting at 0.03, and then how much I'd have to add on to that if I want to allow for uncertainty up to the half, 0.75, 1, and 2 standard deviations. The assumption here is that the Manning's uncertainty follows a standard distribution, and there are links and references to the relevant guidance within the supplementary guidance document. I'd repeat this step for each of my secondary variables, so that could be peak flow, Manning's values, topographic survey, and so on, until I've understood the uncertainty around each. Once I've identified the uncertainties around each secondary variable, I need to know how they affect the primary variable. So how sensitive is that primary variable to the secondary variable? If I change my Manning's roughness, does the peak water level change? If I change the peak flow, does the peak water level change? There will undoubtedly be some secondary variables which are not influencing the primary. This could be, for example, the volume under the hydrograph that's passed down the river, because many river systems are responsive to the peak flow rather than the volume, for instance. If you identify that a secondary variable is not impacting the primary, it can be screened out. The way I estimate the effect of the secondary variable and the primary variable is to do some testing within my model. So I change the value slightly, so I may add a few percent onto my Manning's value or a few percent onto my flow, and I see what the resulting change in the primary variable, the peak water level, is in my model. Once I've undertaken that analysis for all my secondary variables, so I know what the change in primary is for a change in secondary, I can use the equations in the guidance and the spreadsheet provided with this document in order to calculate what the total change in water level is for different confidence intervals. I'll now talk about how the Tier 1 and Tier 1.5 methods deviate in their application of this method. The Tier 1 method is a simple quantitative method. It determines the residual uncertainty for key variables, water level, flow, and it uses a small change test approach to understand the sensitivity of the primary variable to each of the secondary variables. What this means is once I identify the secondary variable, again perhaps roughness within channel, I would change that value by a small amount in the model, say a few percent, and rerun the model to see what the change in primary variable, water level, is. When I go to undertake the calculation, the Tier 1 calculation, that change is extrapolated from that small test and applied to all confidence intervals. It's worth bearing in mind that there are some considerations when taking Tier 1 analysis. Your base model must be your best estimate of your system and avoid being overly conservative or overly optimistic. It's your best estimate of your roughness, your best estimate of your peak flow, and so on. If you include any bias in your initial model, your baseline model setup, you may overdesign or undesign your ultimate scheme. Tier 1 is applicable to initial assessments, strategic outline cases, and perhaps simple OBCs as well. Again, we encourage proportionality when undertaking calculation. There are limitations to the Tier 1 method. Firstly, that extrapolation, that small change extrapolation. The rivers do not always behave in a linear way, and therefore we can miscalculate the uncertainty if we adopt the Tier 1 method. And I'll talk more about that later. Also, the Tier 1 method always assumes a normal distribution of uncertainty in both in the secondary variables. So if you have got a secondary variable which has a non-normal distribution, that's this little bell-shaped curve, then a different method may be appropriate. The benefits of the Tier 1 method are it has a limited number of simulations. You just need to run that small change model once for each of those secondary variables. So if you've got 5 variables you need to test, that's 5 additional simulations. It provides quick insights, it's broadly applicable, and it's very efficient to apply. The Tier 1.5 method is based on the Tier 1 method with some extensions. It was developed by consultants and suppliers following the publication of the 2017 Residual Uncertainty Technical Report. The intent of this is it accounts for the non-linear nature of many systems, so that small change method is removed. Therefore, it provides a more improved understanding of residual uncertainty. It does require more effort than Tier 1 because additional simulations are required. And what that means is, rather than for each secondary variable applying a small change, we instead test each secondary variable for each of the confidence intervals required and then combine the results without extrapolation. So for an example where you had 4 secondary variables, rather than needing the 4 tests you would need originally, you may need 16 tests. So that's 4 confidence intervals for each of the 4 secondary variables. This method is perhaps more appropriate for outline business case or full business case stages of a project, and it gives you a better understanding of the residual uncertainty at varying confidence intervals. There are still limitations, so the method still assumes a normal distribution of uncertainty, that bell-shaped curve, and it requires more simulations than the Tier 1 methods. It's more intensive. It does enhance the detail and provides a more robust assessment of uncertainty, and it allows for better understanding of uncertainty at different confidence intervals. Both Tier 1 and Tier 1.5 are both accepted, but when you're considering which one to adopt, there are a few things to consider. First off is complexity. That Tier 1.5 method is more complex than Tier 1 because additional steps and simulations are required, and as a result, it's somewhat more resource intensive. The trade-off is it gives you far better confidence and a robust assessment of uncertainty than the Tier 1 method, which has that linearity assumption in it. Tier 1 methods are recommended for initial assessments and less critical assessments of perhaps smaller scale schemes, while Tier 1.5 is recommended for outline business case and full business case. But again, there's the concept of proportionality. Consider the best approach for your scheme and for the outcomes you're trying to achieve. What difference does it make? As I say, the Tier 1 method uses the small change approach to calculate the impact on the water level and then extrapolates that out to different confidence intervals, whereas Tier 1.5 calculates the confidence at each confidence interval. If we look at the image on the right-hand side, you can see 2 estimates of the impact of a change in Manning's value on the water level. So on the y-axis, the vertical axis, we've got the water level. Along the x-axis, the horizontal axis, you've got the chosen Manning's values for different confidence intervals. The orange line is the Tier 1 response, so you can see a small change was undertaken and then extrapolated for different confidence intervals, whereas for Tier 1.5, the change in water level was calculated at different confidence intervals. And you can see that's resulted at the extreme, at the 95% confidence interval, in a few hundred mil difference between the 2 estimates, which has a significant impact on your residual uncertainty analysis. That said, the difference between Tier 1 and 1.5 at lower confidence intervals is relatively minor and may not justify the additional time and effort. It's not possible to generalize whether a Tier 1 or 1.5 will provide lower or higher water levels or lower or higher residual uncertainty assessment. We found both in practice, and ultimately the reason for undertaking a Tier 1.5 method is it gives you greater confidence in the outcomes. Just a word on Tier 2. We don't talk about the Tier 2 method in the supplementary guidance, though it is documented in the 2007 report. The reason for this is it's far more complex than Tier 1 and 1.5 methods and likely only to be used for major infrastructure projects where our tolerance for uncertainty is significantly low. There are no known examples of implementation to date, either in the UK or further afield. This method pushes the boundaries of traditional uncertainty assessment and involves complex evaluation of multiple factors, effectively contributing to a Monte Carlo approach where we're running hundreds, if not thousands, of simulations, varying each parameter and developing our own confidence curves and uncertainty distributions. Unlike Tier 1 and 1.5, which assume normal distribution, Tier 2 allows for a range of distributions. The key limitations are that it's generally disproportionate in terms of effort for most schemes and would require significant computational resource and development of a technical approach. The benefits are it allows for non-standard distribution of uncertainty, it further improves the accuracy of our assessment of uncertainty, and enables exploration of multiple scenarios. The learning outcomes from this section of Chapter 3 are an understanding of the different approaches available for calculating residual uncertainty, including their individual benefits and limitations, a discussion of why to choose Tier 1.5 over Tier 1, and a synopsis of how to implement both Tier 1 and 1.5 methods. In the next section, we'll look in more detail at how to apply the Tier 1 and 1.5 methods to a case study. In this section, we'll look at applying the residual uncertainty methods to a simple case study, walking through the analysis and the steps required. The learning objectives for this section are an understanding of the case study and how it relates to residual uncertainty analysis, the steps involved in calculating residual uncertainty using both the Tier 1 and 1.5 methods, a demonstration of how to apply the methods in a practical case study setting, a review of the results and their implications for the project, and comparing the difference and similarities between a Tier 1 and 1.5 method. We've chosen a fairly simplistic but representative case study to demonstrate how residual uncertainty is applied. In this case, we're developing an outline business case for a linear defence scheme. The scheme will provide a standard protection of 1 in 50 years to communities on the left and right banks of a main river over a reach of 1.5 kilometres. We'll be applying both the Tier 1 and 1.5 methods in order to calculate the 38, 55%, 68% and 95% confidence intervals. We're using the existing model developed for the scheme, including glass walls where the defences will be placed, and residual uncertainty we calculate at each node within the model across the reach of interest. The technical approach follows the 5 stages outlined in the previous section. I'll talk through these in summary here and then go into detail about each one and how they're applied. The sections to consider are identify the primary variable, in this case water level, identify and screen secondary variables, define the confidence distributions for each of the secondary variables, quantify the effect of the secondary variables on the primary variable for each confidence interval, and finally calculate the total estimated uncertainty in water level. Stage 1 is to identify the primary variable. As this is a linear defence scheme, the key design consideration is peak water level, therefore the primary variable is water level adjacent to the defences. The next stage is to identify secondary variables and screen them out. Secondary variables are anything that could affect the primary variable. There may be hundreds of these, so it's important we group and screen these appropriately to make the assessment proportionate. By grouping, we look at the example of hydrological factors. So uncertainties at this location are things such as the reliability of the river gauge, the length of record, the assumption of hydrological stationarity, and the appropriateness of the statistical method in calculating peak flows. All those things have been grouped together as one secondary variable, which is ultimately the peak flow assessment for the boundary conditions of the model. Other secondary variables have also been identified and range from the LiDAR uncertainty, bridge coefficient uncertainty, Manning's values, channel bends, and so on. When we're considering secondary variables, we don't need to model them all. Some of them may have no effect on your model, and you can screen them out early on, therefore reducing the amount of work required, or group them together. So for example, in this analysis, the in-channel Mannings and the floodplain Mannings have been grouped together as a single test, rather than being considered individually. Also for this analysis, we've screened out hydrograph volume because the water level is not sensitive to it, some of the channel representation, as well as blockage because it's not a relevant consideration. The next stage is, for every one of the secondary variables screened in, to define the confidence intervals around our uncertainty within these. So how much confidence do I have in the hydrology? How much confidence do I have in the roughness or the topography of the channel? I need to find each of these individually before I can undertake further analysis. We've identified several secondary variables for this project, but I'm looking in a bit more detail at the bridge coefficient. This is how certain we are about the afflux, the change in water level either side of a structure. The default value put into the model was 1, and we've selected a series of values to uplift this by for different confidence intervals, so adding up to 0.02 for a 2 standard deviation or 95% confidence interval. It's often quite challenging to define some of these confidence intervals, and there's really good guidance in the supplementary report under section 3.4.3. This looks in particular detail at hydrology, summarizing the methods required, as well as some of the other key secondary variables such as roughness and topography. It's often challenging to find literature or references to justify the values here, so often we have to rely on professional judgment and skill. Where we have used source literature or used professional judgment, it's always good practice to record our assumptions we've made when we're documenting our analysis. We assess the uncertainty for each of the secondary variables in turn before returning to the next stage. The next stage is to test the model with each of the secondary variables to understand the effect of the secondary variables on the primary variable. How sensitive is the water level to Mannings, to flow, to bridge afflux, and so on. This is where Tier 1 and 1.5 differ. In a Tier 1 approach, we do a single simulation per variable of a small change in that variable. So, for instance, we may increase roughness in channel by a few percent or increase peak flow by a few percent. We see what impact that has on the peak water level and we extrapolate for the confidence intervals. For Tier 1.5, we undertake simulations for each confidence interval for each simulation. So roughness may be run up to 4 times for 4 confidence intervals. This removes the need to rely on a linear assumption. This is more computationally intensive than Tier 1, but there are tools available to optimize this. So for instance, the spreadsheet we provided with this guidance, as well as tools such as Flood Platform and the Flood Modeler API, which allow you to automate and programmatically bring efficiency to what you're doing. As we said before, the choice of Tier 1 over Tier 1.5 or vice versa can have an impact on your results. The image in the right-hand corner shows a Tier 1, the orange line, result versus a Tier 1.5 line below. This shows how sensitive the peak water level is to a change in Manning's value, and that the Tier 1 method may be overestimating that uncertainty by several hundred mil by the 95% confidence interval. The final step is to calculate the residual uncertainty. This is bringing together all the results from step 4 using the equations set out in the RUA guidance. In this example, we've used the spreadsheet tool in order to calculate the residual uncertainty. The tool, which we'll talk a lot more about in the next chapter, provides functionality for Tier 1, Tier 1.5 and hybrid methods for calculating residual uncertainty. Additionally, it allows you to consider up to 4 confidence intervals, multiple secondary variables, and allows you to summarize results. The tool is flexible and adaptable, so you can unlock the spreadsheet and make changes yourself, allowing you to customize the analysis to your needs. The tool also contains ample places to write comments and narrative as to what you're doing, which helps with future QA and sign-off. The final step of stage 5 is to have a look at the results in detail and check they're appropriate and you understand them. Here we've shown these both in the spatial context and the map, as well as the tabular context. The Excel tool has the ability to define reaches, in this case left bank and right bank, where we cluster the results. So the software calculates your residual uncertainty for every node in your hydraulic model. If you're looking at a reach of several kilometers, you may want to group these together for simplicity of understanding. You can see for each group, we've provided the median, maximum, minimum values for each of the confidence intervals. And as you'd expect, the amount of residual uncertainty increases with confidence interval. So from a minimum of 0.35 meters for the minimum 38% confidence interval, up to 1.9 meters for the 95% confidence interval. These are substantial heights of wall to have to add on as freeboard. And again, coming back to the proportionality tool, consider what you're trying to achieve. You don't necessarily have to add that height of wall on. We provide results here for both the Tier 1.5 and the Tier 1 method, and you can see they're broadly comparable, with the Tier 1.5 generally being smaller values than the Tier 1. This isn't a generalization. There are plenty of applications where Tier 1.5 is given higher levels than Tier 1. Another good way of looking at the results is on a map view. So on the left-hand side, we've mapped up the defenses to show where the most uncertainty is, and it can change rapidly over an area. So you may have highest areas of uncertainty immediately upstream of structures where we have little certainty, or areas where we have the greatest uncertainty in Manning's value or channel behavior. Tables and maps are a good way of understanding the results, sense checking you're happy with them, as well as communication to the wider project team and ultimately wider stakeholders. The learning objectives in this section are a greater understanding of the steps involved to assess residual uncertainty and the thought process required at each stage, a greater confidence in the application of Tier 1 and 1.5 methods, an understanding of the advantages and differences between Tier 1.5 and Tier 1, and insights into the type of results that can be produced and an understanding of their implications on a scheme.
Hi, and welcome to Chapter 4 of the Residual Uncertainty Assessment Supplementary Guidance Training Series, Within this chapter, we're going to explore the Residual Uncertainty Assessment tool. The key learning objectives from this chapter are to understand how the tool is organized, to understand how to populate the tool for the Tier 1 and Tier 1.5 methods of RUA, to understand how to interpret the results and outputs, and to understand the tool's limitations and challenges. We recognise that there have been challenges associated with calculation of RUA in the past. As a result, as part of the Supplementary Guidance project, we've developed an Excel-based tool to support with bringing consistency and reliability to the calculation of RUA for both the Tier 1 and Tier 1.5 methods. And I'll show you this tool in just a few moments' time. We've designed the tool with transparency in mind and have exposed each of the individual steps of the calculation. This in turn allows you to easily identify the greatest contributors to the overall uncertainty. The tool is designed around the more commonly encountered use cases, but we've designed it to be flexible and adaptable as we recognise every project is different. Finally, we've designed the tool to allow calculation of RUA for up to 4 levels of confidence. We've provided space to document the decision-making process, and we've also included a list of the commonly encountered secondary variables. This is the tool that's been developed as part of the Supplementary Guidance project. The first thing to note is that the tool is divided into 4 key sections, as indicated by the coloured tabs at the bottom of the screen. Working from left to right, the first section is intended to include more general information associated with the tool itself, for example, an overview of the tool, reference and guidance, etc. The second section is intended to capture the overarching information for the residual uncertainty assessment itself. The third section are those tabs associated with the Tier 1 analysis, and finally, on the far right, are those tabs associated with the Tier 1.5 method. Over the course of the next few minutes, I'm going to talk through each of these sections in turn, focusing primarily on the sections associated with the calculation of RUA itself. This tool is pre-populated with some information, and it's information associated with case study 1A, 1B. I'm now going to walk through the tool, highlighting some key and important information, and also demonstrate to you how to use the tool to calculate RUA. If we look at the general tabs first, I'm not going to spend much time on these because they're relatively self-explanatory, but there are 2 points that I want to highlight. On the Tool Overview tab, there is a Tool Workflow section that outlines the steps and the data that's required for both the Tier 1 and Tier 1.5 methods. Next, on the Contents page, there's a password provided. The tool is provided in a lock state to preserve its integrity, but it's recognized that the tool might not be suitable for all scenarios, and therefore it may be necessary to adapt it. Each worksheet can be unlocked using this password, so you can adapt it to your scheme. Okay, I'm now going to move on to the next section. This section is all about providing the overarching information associated with the uncertainty assessment, irrespective of whether you're completing a Tier 1 or Tier 1.5 approach to RUA. Looking at each of the tabs, the first one, Site Description. This is really just provided as an opportunity or a location for you to provide background information associated with your scheme and your assessment. There's no mandatory information or no mandatory cells that need to be completed in here. One thing that you'll notice that's applicable to all future sheets is that there are now instructions included in the sheets to support you with completing the analysis. This next sheet, Sheet 3, Variable Identification, has 2 key purposes. The first, to record the primary variable, and this information should be entered here. It's worth noting that this information is used in future sheets and therefore is mandatory for the calculation. The second key purpose is to record the secondary variables and the screening assessment associated with them, and this information should be included here. This table has been added as a location for you to record it, but it is not mandatory for the calculation, though in completion is encouraged. This sheet, Sheet 4, Variable Parameterization, is all about defining the secondary variables that you've chosen to take forward into the assessment and defining the confidence distributions associated with each of these. Whilst the sheet's relatively self-explanatory, I do want to highlight some core functionality and also emphasize where data is mandatory for the assessment. Before jumping into it, I just want to also show you that again, there's instructions in this sheet if you do get stuck. By default, these are hidden, but they can be exposed very easily. The first thing that I would encourage you to do is to enter the confidence intervals for your analysis. By default, they're typically these confidence intervals, but you can change them if you want. This information is mandatory. Next, I would encourage you to enter the secondary variable names for each of the secondary variables you've identified as taking forward into the assessment. Again, this name is mandatory. If you're completing a Tier 1 assessment, you also need to include a name associated with each of the small change tests. Typically, this would be the name of the secondary variable and the magnitude of change, for example, flow plus 5%. This is mandatory if you're completing a Tier 1 assessment. The next thing I would encourage you to do is enter a variable unit and the baseline model value associated with each of the secondary variables. Whilst this information is not mandatory, it is encouraged as it's very useful context. The next thing I would encourage you to do if you're completing a Tier 1 assessment, and it's mandatory for a Tier 1 assessment, is to enter the magnitude of change for the small change test. And this is the magnitude of change relative to the baseline or the modeled value. Then finally, the last thing to include is the confidence distribution. So you need to include the magnitudes of change associated with each of the confidence intervals of interest relative to the modeled value. Once you've completed this, you've completed everything that's mandatory for the assessment. There is also opportunity to add justification around the confidence bands, etc., and also to include a subcategory ID if you want to include various confidence bands associated with one of the primary variables. For example, if Manning's N was varying throughout the length of a water course, it would allow you to have multiple secondary variables associated with Manning's N. We now move on to the section of the tool that's intended to support with the calculation of the Tier 1 method to RUA. There are 3 sheets associated with this. The first to store the model results, the second to support with the calculation, and the third to provide a summary of the RUA results for specific assessment locations. If we first start by looking at sheet 5, Tier 1 model results, I think this sheet is relatively self-explanatory, but I do just want to highlight a couple of things. The first thing I want to highlight is that we've color-coded this sheet and future sheets to be able to easily emphasize the data that needs to be required. So the editable cells are these that are highlighted with the lighter blue color coding. So how do you go about populating this sheet? Well, it's really quite straightforward. You first need to add the scenario names of the secondary variable scenarios that you want to test, and these are added into these cells here. You will notice that there's drop-down lists that read from the variable parameterization tab in the tool to support with populating this. The next thing that you need to do, and this is essential that it's added here, is add the assessment locations into column C and the baseline model results into column D. I'd also encourage you to add a link to the results and a comment associated with this model simulation for robustness and all future simulations in fairness. The next thing that you need to do is to add the results associated with each of the small change tests that you've decided to take forward into the Tier 1 assessment. And these should be added into the columns G, J, M, etc. Once you've done this, you've completed the Model Results tab, and you can move on to the calculation itself. Okay, we're now on sheet 6, the Tier 1 RUA calculation. This sheet is actually relatively simple to populate, but does display a lot of information, so I'll walk you through each of the sections. The first thing that you need to do is import the results associated with each of the secondary variables that you want to test. To do this, you first populate column D with the assessment locations. This could be a subset of the assessment locations included on tab 5, the model results for the Tier 1 analysis. The next thing that you need to do is enter the VLOOKUP offsets associated with each of the secondary variables that you want to import. Now, obviously, I've entered this already in this example, but I'll demonstrate how this works quickly now. If we wanted to import the flow results, you would look up the VLOOKUP offset associated with the flow results on the tab 5. So the VLOOKUP offset is 5, and you would enter it into this cell here. This quickly brings in the results, as I'm demonstrating here. You would then do this for each of the secondary variables to pull in the full set of results. Other functionality it's worth being aware of is that you can use a scheme phase ID to allow you to summarize the results across a range of assessment locations. In this example, I've summarized the results associated with a left and right bank defense. If you have scheme phases that overlap, it's possible to enter 2 or more scheme phase IDs as long as they're separated by a semicolon. Now that we've entered all the model results, the RUA calculation itself is automatically completed in the background. I want to talk you through some of the additional sections of this sheet, as there's a lot of information displayed. What we've tried to do is expose the individual steps of the RUA calculation so you can easily identify the greatest sources of uncertainty in your model. I'm now going to talk through each of these sections in turn. So if we move across to the left, the first section that we come across is the differences section. The differences section summarizes the difference between the baseline results and the results associated with each of the small change tests. So those are the small change tests associated with each of the secondary variables. And this is summarized for each of the assessment locations that you've defined on the left-hand side in the results section. One thing to note here is that there is conditional formatting applied that highlights where there's been a reduction in the primary variable. Generally speaking, we only want to take forward the results that are associated with a detrimental impact, and therefore you may want to consider removing these results from the analysis. To do this, you would unlock the sheet and you could delete these results. You would obviously need to carefully consider this and ensure that it's appropriate for your calculation. If we move towards the right on the sheet, the tool reports the partial derivatives associated with each secondary variable for each confidence interval that you've defined in the variable parameterization tab. The reason this information is reported is that it allows you to readily identify the key contributors to the uncertainty. In this instance, the flow and roughness variables are contributing significantly to the overall uncertainty. In actual fact, there's very little contribution from the other variables. This is key information. As I mentioned, this sort of information is provided for each confidence interval. For example, the 68% here, and to the right, we have the 55 and the 38% confidence intervals. To the right of this are the final results for the RUA analysis. This is reported for each assessment location and each confidence interval of interest. We can now move on to the RUA summary tab. The RUA summary tab reports the results associated with the scheme phase IDs that you entered onto in the calculation sheet. There is a drop-down menu here to select the scheme phase IDs that you've entered. And this quickly looks up the results. To demonstrate it, if I was to select the right bank, it quickly pulls in the results and it reports the minimum, maximum and median results across the assessment locations associated with this scheme phase ID. There's also a section to provide notes should you wish to add it. This concludes the Tier 1 analysis, and we can move on to the Tier 1.5 assessment. We're now in the final section of the tool. There are 2 sheets associated with the Tier 1.5 analysis, the RUA calculation itself, and similar to the Tier 1 analysis, an RUA summary tab. The first thing to note is if you're doing a Tier 1 assessment, these sheets aren't required, but they are required if you're completing a solely Tier 1.5 approach assessment, or you're looking to do a hybrid assessment. What I mean by a hybrid assessment is that you calculate residual uncertainty using the Tier 1 method for all of your secondary variables and use this to identify the greatest contributors to uncertainty. In the assessment that we've just completed, we identified that the flow and roughness variables were the key contributors to uncertainty. Because we know that there's a limitation around linear extrapolation in the Tier 1 method, you may wish to refine the results associated with these variables by completing a Tier 1.5 assessment for these alone and combine it with the results from the Tier 1 assessment for the remaining variables. To do this, you can import the results from the Tier 1 assessment using this form here. So Automatically, these cells are populated with each of the secondary variables from the Tier 1 assessment. You then indicate which variables you want to use as contributions to your Tier 1.5 assessment from the Tier 1 assessment. So in this instance, we want to reassess flow and roughness, and we want to pull through the Tier 1 results for the remaining 4 variables. And so we indicate this by adding a yes to the latter 4 variables and a no to the first 2. I'm now going to talk you through how you add the Tier 1.5 results to this worksheet. The method is the same whether you're taking a solely Tier 1.5 approach to RUA or you're doing a hybrid approach that I'm doing here and discussed a moment ago. The results need to be entered into the tables on the right-hand side of the contributions section. Because we're taking a hybrid approach, we need to add results for the roughness and peak flow secondary variables. To do this, and the order that I recommend doing it in, is to first add the scenario name or names, added into these cells here. You'll notice that the confidence intervals are copied across directly from the variable parameterization tab, and this happens automatically. But you do need to manually add the variable change associated with each secondary variable and each confidence interval, and this can be taken directly from the variable parameterization tab. Next, I would encourage you to add a link to the results. This is really just from a robustness and quality assurance perspective. The next thing I would encourage you to do is add the assessment locations. If you're completing a hybrid approach to RUA, I would encourage you to ensure that these assessment locations are the same as in the Tier 1 analysis. The next thing to do is to add the baseline model results, and these should always be added into column J. These results are copied forward automatically into the tables on the right-hand side. The final things to do are add the results for each of the confidence intervals for each secondary variable that you're wanting to test. And you would add these into these columns here. The final thing to do is to add the scheme phase IDs if you're wanting to summarize the results for multiple assessment locations. You've now entered all the results that are required for the Tier 1.5 assessment. Similar to the Tier 1 calculation sheet, the Tier 1.5 calculation sheet reports the partial derivative information from the RUA calculation associated with each of the confidence intervals that you defined in the variable parameterization tab and each of the secondary variables that you've chosen to take forward in the analysis. This information is critical for understanding the magnitude of uncertainty associated with each of the secondary variables and identifying where the greatest sources of uncertainty are. If we move further right on the sheet, the next section that I want to highlight is this section here. This section is a summary of the contributions from the Tier 1 analysis for the variables that you selected earlier on in this sheet. The final section of this sheet are the overall residual uncertainty allowances and this summary table. The residual uncertainty allowances are summarized at each assessment location for each confidence interval of interest, as defined on the variable parameterization tab. This then brings us to the final sheet, sheet 9. This sheet supports with summarizing the Tier 1.5 results if you've chosen to use scheme phase IDs. To use the sheet, simply add the scheme phase IDs into these cells here. This can be done simply by using the drop-down list provided. The tool then summarizes the results from the assessment locations associated with each of these scheme phase IDs and provides the minimum, maximum, and median results. The tool also provides the Tier 1 results for comparison. This now concludes the tool walkthrough. I do hope that you found it useful. Now that you've seen the tool, I hope you too agree that it should support with bringing consistency, reliability, and also efficiency to the calculation of RUA. Before I finish, I just want to emphasize that Flood Modeler can support with bringing further efficiencies through application of its existing and future functionality. There's currently the batch simulator, which is ideally suited to managing the simulations required for a residual uncertainty assessment. There's also the Flood Modeler API, of which I supported with the development of and am very passionate to see adopted in our industry. The Flood Modeler API essentially allows you to programmatically interact with Flood Modeler via Python, which ultimately gives you the capability to make custom tools. You could essentially make one custom tool that supports with a full residual uncertainty process. In terms of future functionality, there's Flood Platform. This is a really exciting development, and it will support with managing the models, the data, the simulations, and ultimately the results. And I hope in the future it will also be able to support with the full calculation of RUA. Now that we've completed the chapter, I hope that you have an understanding of the applicability of the tool, how the tool is organized and how you go about using it, and also you will have an understanding of its limitations and constraints.
Reflections and further information. Future areas of research and improvement. There are still areas where we require further knowledge, experience, or policy decisions to fully implement residual uncertainty. Only after this additional work can we consider how these areas are brought into future RUA guidance. Appendix A of the Supplementary Guidance provides recommendations for further research or FCRM policy decisions on some specific themes. These themes have been discussed throughout this training package, but to summarise, they include the role of RUA for existing defences, requirements for adopting specific confidence levels, how to robustly apply the Tier 2 method, coastal wave run-up and overtopping, surface water systems, NFM, and the application of RUA to flood storage schemes. The project team also wish to highlight some areas where the Environment Agency and the wider UK modelling industry should be seeking to take a continuous improvement approach to how RUA is undertaken. For example, in the Environment Agency, we are considering how to build more structured sensitivity testing of our models into project requirements through a review of the standards we set for model sensitivity. The RUA Excel tool was also only ever intended to be a beta tool. We encourage feedback on its use and have deliberately left it as an open tool so others can adopt and build on its functionality. We are keen to see how RUA can be developed further across the industry in terms of using the APIs and software development. Accessing the Residual Uncertainty Assessment Guidance. These are the literature reference numbers for the full Supplementary Guidance pack and tool. Please use these reference numbers when searching for or requesting copies of the guidance. The guidance document package is available via Content Cloud for Environment Agency users, the Collaborative Delivery Community Hub under Evidence and Risk, Modelling Standards and Guidance page for any Environment Agency framework suppliers, or can be requested via enquiries at environmentagency.gov.uk for all other users. If you have any technical queries or wish to provide feedback on the guidance or tool, please contact the Modelling Skills and Quality Assurance team on msqa@environmentagency.gov.uk. And just a reminder that the Accounting for Residual Uncertainty and update to the freeboard guide, which is the original 2017 science report, is available on gov.uk.